No. Unfortunately, you have to buy it, but fortunately, it's not very expensive.
Oh, so it's that paper booklet.
Yeah, it has a yellow cover on it, and it's plastic shrink wrap.
Do you want to?
Yeah, yeah. How much was it?
No, I just was like, I'm not even gonna look. I wasn't even gonna look. I was just like, I'm just gonna buy it.
Yeah, this is it. I mean, it's cheaper just to buy it already printed out like this than to print it on a printer. So this is what you're looking for. Thank you. I just scanned it, so I have a PDF copy of it, but there are electronic copies floating out there. You know, if you want to go that route. But I don't have it. I can't post the electronic copy on Canvas because bookstore would not be happy. All right. Were there any other questions? So I'm going a little bit out of order. The reason I'm going to go a little bit out of order is because it's because I want you to have the maximum amount of time to memorize stuff. And so we might as well start, especially if this is going to be a 3-day weekend. On Monday's a holiday. And so it'd be good to or I don't know if you can do it over President's Day weekend, but you might look at it and see. But there are a lot of periodic tables out there with a lot more information. I mean, this is one of the best ones out there, Sergeant Welch periodic table. They sell these in bookstores all over the U.S. But this has the information on charges. So sometimes there are multiple charges. For example, nitrogen. Nitrogen's charge varies from -3 to +5. But what they're showing here are the most common charges. The most common charges would be a -3 and a +3, and we'll have less common charges there that are bold. So fluorine, -1. These are no charge, noble gases. But chlorine's charge varies from -1 to +7. Do you see that? There's a pattern with this. When we're looking at the charges, we can get it from the periodic table. And so let me talk about this little pattern here. And there are two things that we try to remember off the periodic table regarding charges. One are the common charges. The common charges we usually get based on its position in the periodic table here. So these are the common charges. So for example, chlorine, which is Cl, -1. In fact, all these are -1 here. And then oxygen, -2, etc. So based on its position in the periodic table, we can figure it out. But others are going to have other charges that are available, but maybe not as common. And so we want to know what the range of charges is. And to figure out the range of charges, so for example, carbon here, what does the charge on carbon vary from what to what? And so we can take a look. Sergeant Welch periodic table here. Oops, that's not it. Here. And tell me what the range of charges goes from for carbon. Yeah, it goes all the way from -4 to +4. And this isn't even all the charges. So we have -4, then we could have other ones like +2, +1, 0, etc. And so we want to know the range, and we want to know the most common charge or most common charges. Now, to figure out the range, there's a pattern to this as well. And so we try to look at the pattern. Chlorine goes from -1 to +7. And what is that related to? -1 plus 7, how many digits is that? -1 to +7, how many units is that? 8. Oxygen ranges from, actually, look at sulfur. Sulfur ranges from -2 to +6. How many is that? 8. Phosphorus goes from -3 to +5. 8. Do you see? They're all 8. So the range is 8. Now, how do we figure out what that is? Carbon -4 to +4, that's 8. And there's an easy way to figure out. When it has a negative charge, that means it has an extra electron. Because electrons are negative and it's a subatomic particle, so if we have an extra electron in the atom, it's going to have a negative charge. Extra 2 electrons will have a -2 charge. And so fluorine, later on we'll learn this, but fluorine has 9 electrons. And if it gains 1 more electron, then how many electrons total does it have? 10. And oxygen normally has 8 electrons. If it gains 2 more electrons, it's going to have, it's going to have a -2 charge and a total of 10 electrons. Nitrogen has 7 electrons, and if it gains 3 negative charges or 3 electrons, it's going to have 10 electrons. And so the pattern is this. The pattern is this. The noble gases are special. The noble gases are special because they're very stable. Like they used to call them inert. Inert means they're very unreactive. And they're extremely stable, non-toxic, except for asphyxiation, which shouldn't kill you. And so these, people have these helium mixtures that they use in scuba diving and whatever else. You inhale this stuff, breathe this stuff, essentially. And so there's a connection to the noble gases. And there are 2 ways to get there. So for example, here, chlorine's charge ranges from -1. So -1 means it has an extra electron, so that it goes from 7 to 18. And then it goes +7. How do we get +7? Well, if we lose 1, that's +1, +2, +3, +4. I'll jump over here, +5, +6, and then we're at +7. So we go from 16 electrons to, where are we going from? Here, 17 electrons to 10 electrons. So how many did we lose? 7. And so that's where the range comes from. The range comes from how many does it take to get here, or how many does it take to lose to get there. And so carbon's kind of weird because carbon's right in the middle. If carbon gains 4, that is 6 plus 4 gives us 10, we're there. If carbon loses 4, 6 minus 4, we're here at helium. Do you see that? And so the carbon range for charge is from +4 to -4.
So to summarize, they're trying to get to this end of the periodic table.
Right. And so if you're on this side, it's closer to gain.
Yeah.
If you're on this side, it's closer to lose. If you're right in the middle, then either way, gain or lose. And so let's take a look at this. Do you see all these gains? We have to gain 1 here, we have to gain 2 here, we have to gain 3 here. Here we'd have to gain how many? 4. And so carbon with a -4 is called carbide, although they're not making you memorize it, but carbide is very common. That's carbon with -4. And so that's kind of in the middle. Then boron would have to gain how many? Carbon would have to gain 4, boron would have to gain 5. It's hard to take electrons. It's not like there's electron that are given freely. Boron would have to do something called oxidize. It has to take the electrons. Oxidation is taking the electron. Boron's just not very good oxidizer. And so it has a hard time taking, and especially that many electrons. If it has to take 5 electrons, it's got to be a powerful oxidizer. It's got to really take the electrons, but it's not. UCLA had one of the major boron researchers in the world. It's Professor Hawthorne there. I remember him because I remember his car. He had this 280Z sports car, and the license plate read like Dr. Boron or Mr. Boron. It's one of those vanity plates, so it's easy to remember. But anyway, he was interested in these boron-carbon cages, and so these are like spheres that are made of boron and carbon atoms put together like a ball, a buckyball or soccer ball or something like that. And what he's trying to do with these spheres is he put a radioactive atom in there. Radioactive atoms are unstable. They break apart. because of the structure. The structure isn't particularly stable. And the research that at the time was he was trying to get these to get absorbed by tumor cells, cancer cells. And so it was like a Trojan horse. It would be absorbed by the cancer cell, and then he'd shine light on it. And some of the bonds are quite weak, so just visible light was enough to break open the cage. When the cage breaks open, the radioactive atom is free to go and kill the cancer cell. And so if those can get preferentially absorbed by the cancer cell, then that's a way to kill the cells using that kind of Trojan horse method. And hopefully the healthy cells don't pick it up, these cages. But anyway, it's boron. So boron, it's probably a lot easier to lose because if it just loses 3, then it's like helium. And the same thing, when we get to beryllium, it's easier to lose because beryllium would have to gain 6 electrons. That's a lot of electrons to have to take. And then lithium loses 1. So these ones tend to lose. These ones tend to gain. And then here, if you have manganese, how many would manganese have to lose? What Roman numeral is manganese?
It's 2.
Roman numeral.
7.
7. And so how many would manganese have to lose? 7. That's a lot to lose. And so manganese losing 7 isn't as common. And so these are what we call the common. You know, maybe it loses 2, maybe it loses 3, you know, but the more it loses, the harder, the tighter it holds on to its electrons, and the more difficult it is to take them away. So there is potential for losing up to 7, you know, but it's going to be very difficult. What Roman numeral is iron? 8, and they have to lose a max of 8. That Roman numeral, and the reason why I say the Roman numeral is useful to know is the Roman numeral corresponds to what we call the max positive oxidation state, the maximum positive oxidation state. It's a useful number to know because going beyond the max is very difficult. Going up to the max can be difficult as well, but possible. Well, anyway, these I already talked about. What we want to do, and let me talk a little bit more about memorization, especially before long weekends. I'd like to do that. But we know the common charges here, and the common charges, we don't really have to memorize too much. I mean, 2, 3, 1, 2, 2, 4. This is 3, 5, very common. Plus 3, yes, but ultimately plus 5, it could be, plus 3, 5. So we can see that, and when we look at these other periodic tables, we can see that here. Let's take a look at this other periodic table. So manganese is in group 7, and plus 7 is its mass. Technetium, plus 7. Interesting, technetium is another one that's used for treating cancer. It's radioactive. You see, this shows this TC is hollowed. All these are all hollow. Those are all radioactive. Radioactive atoms are unstable. They don't last very long. Technetium. Technically, these should be plus 8, but it's very difficult to get that high of a charge. Maybe in ruthenium, iron's a little smaller, so iron's going to be more resistant to losing all 8. But something like ruthenium is a little bit bigger, so it can potentially go up to 8. Osmium, potentially up to 8. The oxidation states of these are a bit different, though. Although this shows a max of 1, this is group 1, E. It shows a max of 1, but this one goes to 2. There's theoretical reasons for that to better understand the silver one. Ag silver. Silver is max is 1, like that. And gold, there's a reason for gold going up +3. +3 is actually more common than +1. But this is somewhat helpful. This is more helpful. Zinc never goes beyond 2. In fact, there's only one charge for zinc, and that is 2. Same thing with cadmium. Mercury is 1 or 2 Hg. And so as we go along, we can get more and more information, but initially we want to know this, and we're going to use the periodic table to tell us this. And so these are called fixed charge ones over here, fixed charged over here. These are variable charge here, but all of them technically are variable charge. It's just, a variable charge, and that is, they show other charges. But these ones are much more commonly variable charge. So things like chromium +2 +3 is very common. Manganese, manganese actually +2 +3 +4 +5 and +6 and +7 for manganese. But some of those higher ones are stabilized. I'll talk about how they're stabilized differently. There's a difference in how we name these things. If we have fixed charge, then, like zinc, the only charge on zinc that we worry about is 2 plus. And when we have fixed charge, we just call it the zinc ion. The cadmium ion. Cadmium is always 2 plus. The sodium ion. That brings up confusion, because if I just said zinc, you don't know if I'm talking about zinc ion, that is the charged atom. Charged atoms are ion, or zinc, just the plain old atom. Zinc, the plain old atom, has no charge. It has the right number of electrons and the right number of protons, so there's no charge. And so we usually use ion. But for these variable charge, we incorporate the Roman numeral. So I don't know, if I'm talking about the chromium ion, which one am I talking about? Am I talking about +2, +3, or one of the others? +2 or +3, we use a Roman numeral. So if I'm talking about chromium +2, I call it chromium, parentheses, Roman numeral 2, close parentheses. And so that's chromium 2. And then the same thing, chromium 3 would be chromium, Roman numeral 3. Have you heard of chromium 6? Chromium 6, have you heard of Aaron Brockovich? Have you heard of Hinckley, California? Hinckley, California, which is in the San Joaquin Valleys, like south of Bakersfield, there's cancer cluster there. And so there's a very high rate of cancer. And there's a law firm, and Aaron Brockovich was a secretary. They made a movie. I think the movie's called Aaron Brockovich. Can't remember. But they're trying to figure out, why is there a cancer cluster there in Hinckley, California? It was 2000, so it's 24 years ago. Julia Roberts played Aaron Brockovich. This is the real Aaron Brockovich here. This is based on a true story. But Aaron Brockovich was apparently, I guess, in Hinckley, California. You know what they attributed the cancer to? The water, the groundwater, was contaminated with chromium 6. And chromium 6 is kind of reactive. It would be chromium Roman numeral 6. Let's see if they talk about it here. Chromium 6 is like, sometimes they'll write it like this. That's not really how we write it. We write it chromium, the whole word, and then parentheses, Roman numeral 6, close parentheses. But these are shorthand ways of writing it. Chromium 6, chromium -6, or they call it hexavalent. Hexa means 6, valent is a charge. Hexavalent chromium, also written as chromium 6. Well, chromium 6 is a carcinogen. Chromium 3 is not. If you have chromium 3 or chromium 2, you're okay. But chromium 6, its properties are quite a bit different, because it's lost so many electrons. And the chromium 6 is not alone. It's usually with other things. We'll talk about that later. But anyway, this turned into a big case against PG&E, Pacific Gas and Electric. I guess they were dumping. The chromium-6 was used in, I think, the transformers or something, and they're dumping the liquid there, something like that, into the ground. It was getting in the groundwater. Chromium-6 is in a lot of things, though. It's in concrete, like concrete powder. One day, my backyard had a thick layer of dust, concrete dust. Next door neighbor was pouring concrete, and this gigantic dust cloud. And I was thinking, oh man, all that chromium-6 inside there. Didn't want it, so I was thinking, oh, hopefully it'll rain soon or something. And then leather tanners, people who tan leather, they use chromium-6 to tan leather. Chromium-6 is what we call an oxidizer. If you lose that many electrons, then you want electrons back. And oxidizers like to take electrons. You know what? Some powerful oxidizers over here on this chart. These are some powerful oxidizers. So, for example, F2 is the most powerful oxidizer on this chart. This is the element fluorine. Do you know what H2O2 is? Hydrogen peroxide. Hydrogen peroxide is the number 2 oxidizer on that chart. And you wouldn't think hydrogen peroxide is all that big of a deal because you can buy it at the supermarket. But when you buy it at the supermarket, it's only 5% hydrogen peroxide. I was reading this story about hydrogen peroxide because did I tell you about the UCSB, the professor who wanted to get rid of the 50% hydrogen peroxide, dumped it in the seawater? They dumped it in the seawater. They figured, okay, hydrogen peroxide, when it reacts, it's just going to form water and oxygen. So water and oxygen, that's fine. It forms that. And so they ended up doing that because they're afraid of the risk. There's a risk to hydrogen peroxide. And so I was reading, this was many years ago, but I was reading one story about hydrogen peroxide. It's used for other things too, the more concentrated stuff. The 50% stuff, some people use it to bleach hair. Yeah. And then other people use it in the garden. And so there's one avid gardener, and they found a great deal on hydrogen peroxide in San Diego, but they wanted to take it home with them, but they flew. And so what they did was I think they bought in bulk. So they packaged it in like a plastic milk jug or something like that. And they put it into a plastic ice chest and then taped it up. And this is pre 9/11. So they were able to convince the whoever checks in the baggage check, they were able to convince them to check it. And so they put it into the luggage compartment of the plane, and then as they were flying, this from San Diego, I think it was Northern California, they were flying, or I can't remember, maybe Sacramento. But as they're flying, the cabin began to fill up with smoke. And so apparently the hydrogen peroxide leaked out of their plastic 1 gallon container, leaked out of the ice chest. It must have been a pretty cheap ice chest, and started dripping on fabric luggage. When it started dripping on fabric luggage, it started to oxidize it, it started to burn it, and then eventually caught on fire. And so they did an emergency landing, but fortunately nothing became of it. I mean, it was just that. And then after that, no more hydrogen peroxide on that. But that's quite dangerous. I wouldn't, if that person knew how powerful of an oxidizer that is, do you think they would have risked their life, checking in hydrogen peroxide?
Some people would.
Yeah. Anyway. Yeah. So anyway, this is this whole story. Yeah, quite a thriller. There was a lot of litigation. There was a lot of how can you be certain, with what certainty do you have that the chromium-6 caused all the cancer cluster there? And it's hard to, pinpoint the blame. So
There's a place like that in Downey because of all of the aerospace stuff.
Oh.
Because Downey was where NASA used to create all of their.
So is it like a Superfund, EPA Superfund site there?
It's like this. Mm-hmm. It's random because there's all these little the little starts with P and I'm blanking, but they're all these little stores and stuff like that, and then a promenade. So there's these little promenades, and then there's just this big old empty lot.
Oh, right.
And no one wants to touch it because a lot of the workers that were when they were like cleaning up the
Mhm.
sites and stuff, they got cancer, they got lung diseases, they just got really sick, they got chronic illnesses. So we're like, that's just not good.
Yeah, that's a good idea. I mean, a lot of this stuff is kind of hard to predict. I mean, around here, the South Bay, beryllium has a bad reputation. Beryllium's here. Magnesium, what magnesium is used for? Magnesium was like a lot of people I have a magnesium bike or something like that, or magnesium this, magnesium that, because it's a very lightweight metal. And so in aerospace, beryllium was used because it's very light. The atoms don't weigh that much. And so all the people were machining beryllium, and it wasn't like they got sick immediately, but eventually all of them died. And it turned out that beryllium is extremely toxic. They didn't know this at the time, otherwise I don't think they would have been machining it. They found out later. And the problem with beryllium is because it's so light, it has a very small size. And beryllium's like magnesium and calcium. We need magnesium and calcium to function. And what happens is the beryllium gets in there and replaces the magnesium and calcium with beryllium. And it behaves differently because the electrical attraction is much stronger between beryllium and whatever else, the protein, than magnesium and calcium. Magnesium and calcium are bigger. Magnesium is like this, calcium is like that. And so the electrical attraction, the coulombic or electrostatic attraction is much weaker. And so that screws everything up. And so this is why they ended up dying from exposure to that. And so that happened in aerospace. There's chromium-6, and then there's a bunch of lead contamination south of downtown. There's a super fun site there. Even on Artesia Boulevard, near Artesia and Normandy, if you look on the right there, there's a big pond, and the pond has a thick layer of asphalt on top of it. Have you seen that? That thick layer of asphalt is to prevent anything from vaporizing off the pond, because that pond is a dump of toxic waste, basically, there. And then as you're driving out to Mojave on the left, there were ponds there that they used cyanide to extract gold and silver out of there, and they're worried it was blowing across the highway 14 there, so they covered those also. But that's not the great part of chemistry, but yeah.
Let's hope we don't die.
So there've been industrial. This is why things like like the whole idea of a lab leak should have like lab leak was there's lots of lab leaks and those types of things, and you got to prevent those from happening in the future. The worst case of a lab leak was in India, Bhopal. Have you heard of that? Okay. This is probably too long ago for you guys, but Bhopal. This is the worst industrial disaster in the world, I think. It's a lab leak, methyl isocyanate gas. And how many people died? $3,787 deaths, 574,366 injured. That's just from one accident. Can you imagine you're the one person responsible for that lab leak? Or maybe it was, I don't know if it was human or mechanical failure, but even if it was a mechanical failure, there should have been backup systems there, right? Don't you think you'd want to study the heck out of this to make sure it doesn't happen again? What failed? How did that much stuff escape? And so, I mean, to have 4,000 people die in one accident, that's pretty horrendous. But that was Bhopal. So, this type of stuff we want to know. Everybody wants to know. And for chemistry accidents, they're often published. For example, a recent one was an explosion. I talked about explosions, right? There was one at the University of Hawaii where I think the professor, they were working with hydrogen gas, and it exploded, and they ended up suffering fatal injuries from that. At UCLA, there was a person who just graduated and was taking a gap year before starting medical school. And so they wanted to go to UCLA and work in a research lab. And so they did, but they were working with things that are quite unstable. They're pyrophoric materials. Pyrophoric materials, the instant they touch air, they catch on fire. And so you have to work with all the kinds of special techniques and equipment to handle what we call air-sensitive compounds. And when you're doing certain things, you could do it the quick way, the quick, rapid way, or you could do it the long, tedious way. So they're trying to transfer a pyrophoric liquid from one container to another. And so one quick way of doing it is using a syringe, because a syringe will minimize the contact with air. So they pulled up some liquid out of a container. This container is sealed, and it had a nitrogen atmosphere over it. They didn't want oxygen. Nitrogen was okay, and air consists of nitrogen and oxygen. Nitrogen is not going to support combustion. So, for example, when we did the Bunsen burner, we needed to mix the methane with oxygen, not with nitrogen, because nitrogen is not going to do anything. Nitrogen is what we call a pseudo-noble gas. Nitrogen is very unreactive, like these. And so we inhale air with 80% nitrogen, roughly. And it does nothing. It's like inhaling helium. Oh, helium will change your voice, but nitrogen, when we're used to nitrogen, density, and whatever else. And so it's a pseudo-noble gas. It's an honorary noble gas because it's so unreactive. Noble gas is totally unreactive, totally stable, that kind of thing. And so it was most likely under nitrogen because nitrogen's cheap. In all the buildings in research labs, they use a lot of liquid nitrogen. All these if you go to a research lab, there's a gigantic tank outside filled with liquid nitrogen, and that liquid nitrogen's constantly boiling because the temperature's too warm. It's like at room temperature outside, but it's heavily insulated, but you can't stop it from boiling. So every lab has plentiful free nitrogen gas. And so you can just blow a whole bunch of nitrogen, blow the air out of there. And so they poke a syringe in here and then withdrew it. But the problem is let's say if you use a 10 milliliter syringe, do you want to put 10 milliliters in there? No, you want to put like 1, 2, 3 milliliters. You just want to use a little bit of the capacity. What they did was they used a syringe that's way too small. If you use a 10 milliliter syringe to get 10 milliliters, then the plunger can come out easily at the back end, and you don't have much room to play with, right? And so anyway, I think it was a situation where they used a 10 milliliter syringe to extract 10 milliliters. And as they were doing this, they pulled the syringe out, and then the plunger was going in and squirting out the liquid out the needle. And then it caught on fire, so it's a little flamethrower. And then they were wearing not cotton, they were wearing, and that caught on fire. And so they suffered third-degree burns, I think over 80%. And and then it was like, I think 2 weeks later, they finally succumbed to their burns and died. But it was just like, just graduated. And so, if you work with dangerous stuff, then you should have the appropriate training. So that's one of the things they're doing now. They're doing a lot more training. When I was at UCLA, I worked with a lot of dangerous stuff there. But I didn't work with the most dangerous stuff. The people that worked with the most dangerous stuff were on the roof. They were on the roof, so if their lab blew up or the lab caught on fire, it wouldn't affect the whole floor. And so, I was working on the third floor, I think. But still, potential for explosion. Fortunately, I didn't have any explosions, but when I went to UCSB, I had three explosions. One explosion was pretty loud, and so a whole bunch of people came running to the lab to see what happened, but I was okay.
Were they your fault or were they?
It was my fault, yeah. That was not as bad as UCSB. Another person had an explosion. They're carrying a beaker, which is a glass beaker. An explosion almost severed their thumb off, so the thumb was just hanging by the skin there. That explosion brought in the FBI. The FBI came in, they arrested him, and then they interviewed everybody because they thought he was making explosives for like terrorist action. Yeah. You know what he's making explosives for? He's actually making explosives. He's making explosives to try to make synthetic diamond. This was all like side. This is side reactions that they were doing, all kind of, I guess, illegal. Yeah, because these weren't. But in a way, not illegal because it's a research lab. In research labs, you try to do things. So they're trying to make synthetic diamonds. So they're trying to shape a charge for implosion. So they put carbon graphite in there, and then they shaped the charge, and then they brought it down to the beach, and then ignited it, blew it up, imploded, and then they dig through the ash to see if any diamonds had formed. That's what they were doing. So that's kind of cool, but he almost lost it, and then that was the end of their diamond, their get rich scheme or whatever they were thinking.
Yeah, I could have stopped.
Yeah, if we had to stop. Yeah. I mean, it was pretty serious. Well, anyway, so we learned patterns. So these aren't all the charges here. I mean, there could be more charges, and then the things get more complex because some of these charges, these are what we call the monatomic ions here. Now, the monatomic ions, the naming, we'll talk about the naming for those. And so what I do here is, so when I'm dealing with a monatomic ion, I don't memorize. This is, I think I mentioned this, and this is how I memorize them. I memorize them all separately. I didn't associate them with any pattern. I just made these kind of flashcards or wrote it down repeatedly.
Canvas for us to be able to access.
This is not on Canvas. Okay. But it's in the yellow pack. Okay. This is the supplement. And so if I know the name, then I know it. And then did I mention I'm not going to hold you responsible for the old names? Did I mention that? Yeah. Just the new ones, the Roman numeral. We only have to use Roman numeral if there are more than one, if there is more than one common charge. We don't use a Roman numeral if there's only one charge. So for example, barium only has one charge, 2+. Silver only has one charge, +1. Zinc and cadmium only have one charge, +2. So you need to know where the variable charge ones are and where the fixed charge ones are. And so here we can kind of see, over here fixed, up here fixed, and then in here is all variable. So anything in this area we have to use a Roman numeral with, except for a little island of fixed charge. So anywhere in here is variable except for silver, cadmium, and zinc. These three we never use a Roman numeral for because there's only really one common charge for those. And that's because it's group 1 and group 2, so that's helpful to remember. It's group 1 and group 2. So that's some memorization there. Now, those are the ones on the left where they lose. The ones on the right, they gain. And so these ones we can kind of figure out. Hydrogen is kind of in the middle too. It can gain or lose. But what we do with the name is we just change the ending. So if it's gaining electrons, it forms a negative atom, and the negative atom is called an anion. So this is what I call it. And it's only one atom, so these are the monatomic anions. And so these ones we already know the charge based on these positions in the periodic table. The name is pretty easy that we just changed. This is bromine, it's changed to bromide. Chlorine gets changed to chloride, etc. Sulfur gets changed to sulfide, oxygen to oxide. This is it. And these need three: nitride and phosphide. And so those I wouldn't even create flashcards for. Those I just do off the periodic table. So I'm trying to minimize the amount of memorization I do. What about these? What should we do with these? What we should do with these is there's another pattern based on the periodic table, but it's not in the supplement. And so let me talk about that now. So the first thing is, maybe let's just look at the observations and see if we see the pattern. And so scientists spend a lot of time looking for patterns here. Can you see a pattern in there? Or patterns? Mm-hmm.
When there's like oxygen, most of the time it has an 8.
Yeah. When there's an oxygen, it has an 8. That's correct. And so let's look at all the 8s and let's see if that's true. Now, can we tell how many oxygens it has? So if we go here, acetate, 2 oxygens, chromate, 4 oxygens, dichromate, 7 oxygens. We see oxalate, 4 oxygens, permanganate, 4 oxygens. Is there a pattern to the number of oxygens? Well, it turns out all the 8s will have oxygen. And so that's a good pattern. But do you see a pattern in the number of oxygens? Well, what's the range of oxygens that we're going to see? Yeah, something like that. 1, actually 1, maybe not 1. You see?
What hypochlorite? I had hypochlorite.
Yeah, this is an 8. And so 8 is different than an 8. An 8, the oxygens are going to range from, what's the fewest number of oxygens in an 8 that we see? 3. Acetate, here's 2. 2 to 7, it looks like. The ides are going to also have oxygen. You see that? And then we have the ides. The ides don't necessarily have oxygen. And so, all right, let's continue this here. And so what we want to do is we want to minimize the amount of memorization. So we talked about the ides here. All we do is when we look at it, the element, we look at its position in the periodic table, and we can get the charge, and we can get the name by changing it. And so the monatomic anions are like this. They're all the ides. There are some ides that we have to memorize. And so let's just look at the ides that we have to memorize. These are not ones that we can get off the periodic table. These are ones that we'll just have to memorize. And so it's a polyatomic ide. A polyatomic ide has more than 1 atom. And 2 atoms should be different. And so the first polyatomic ion is cyanide. This one we aren't going to be able to get off the periodic table like chloride. Chloride's no problem. It's chlorine with -1 charge. Cyanide we just have to memorize. So what's the best way of memorizing something like cyanide? There are different techniques for memorizing that. And so we got the cyanide. We have the next one here is hydroxide, and we have the last one here, peroxide. And so these ones are just straight memorization. So let's talk about that here. And so these are the ides that you have to memorize. Not on the periodic table. The first one is 1 carbon, 1 nitrogen with a minus charge. So it's a carbon bonded to a nitrogen and has an extra electron. This one is called cyanide. And then we have an oxygen bonded to a hydrogen, also with a negative charge. This one's called hydroxide. And then we have 2 oxygens bonded together from a 2 minus. This one's called peroxide. Peroxides are quite unstable. When you have an oxygen-oxygen bond like that, it's weak and it's easy to break. So peroxides, you even have to protect from visible light. We don't want light to break the bond. And so these ones are just straight memorization. So however you want to do this is fine. You could use flashcards or you could write it. My preference is just to write it over and over to get it ingrained in your muscle memory. But cyanide, hydroxide, and peroxide. Those are memorized. Okay, what else should you memorize? Okay, we're going to move on from ides to eighths. And we're going to look for patterns, as many patterns for the eighths as we can, and then try to minimize the amount of memorization. But there are 2 eighths that I want you to memorize that are not on the chart. The reason I want you to memorize these 2 eighths is because they form a pattern on the periodic table. One is the element B. Element B is what? Boron. What group is boron in? Roman numeral. What Roman numeral group is B in? 3. So, yeah, it would be in group 3. And boron forms an ion called borate. You might have heard of borate. There's some borates like in eye drops, I think, and other things. But the borate has 3 oxygens and a 3 minus charge. The reason I bring up the group number is to help you remember it. Because it's 333. Do you see 333? Borate is group 3 with 3 oxygens and a -3 charge. So this is borate. Borates have a history in California. There used to be a soap called borax. Actually, they still have it, borax. People use borax soap for laundry, yeah. They used to use it for washing hands. I think some people use it for slime. What is that, slime or whatever that is? Yeah, slime. Yeah. So it's making a comeback. Anyway, but there's boron in California, the town of Boron, and there's dried lakes that are full of borates in them. All right, so that one you have to memorize, just borate. What's next to boron? carbon. And so what we want to do is we don't want to have to memorize carbonate. I don't want to make a flashcard, and then I don't want to write this 500 times. And so I want to know, what is carbonate? And so what we need to know is, how many oxygens does carbonate have? Well, it turns out carbonate has, not 2, it actually has 3 oxygens, the same number as borate. But the charge is not 3 minus. Do you know what the charge on carbonate is? 2 minus. So this would be carbonate. And then next to carbon is nitrogen. And so what we want to do is we want to try to figure out what nitrate is. And do you know how many oxygens nitrate has? 3. And the charge, -1, which we just call negative. And so this would be nitrate. Do you see a pattern here? Yeah. Then oxygen, there's no oxate, so we'll just draw an X through oxygen. And then we go from oxygen to fluorine. And so we'll try to figure out what fluorate should be. How do you spell fluorate? F-L-U-O-R-A-T. How many oxygens do you think fluorate has? 3. Yeah, it should have 3 oxygens. Now the tricky thing is, what is its charge? You'd think it'd be like +1, maybe 0, if it goes 3, 2, 1, 0, +1, something like that. But it doesn't. Do you know what its charge is? It's -1. -1, well, once we hit the floor of negative anions is -1. What's the lowest charge you can have on an anion? -1. And that's where it ends up. Now, what we're going to do is we're going to start working down. You know what's below fluorine? Chlorine. And so what we want to do is we want to figure out, what is chlorate? And so what would you guess the number of oxygens on chlorate to be? It turns out, yes, 3 is correct. And what about the charge? Yeah, it's bottomed out. The charge is bottomed out at -1. So that's chlorate. And then below chlorine is Br. Br stands for bromine. So we're going to look at bromate. How many oxygens do you think bromate has? 3. And its charge? It's actually negative. Again, it's bromate. And then we'll just do one more. I stands for iodine. And from that we can get iodate. Iodate is going to be IO 3 minus, yeah. So what we do is we try to minimize the amount of memorization. So if you know what borate is, can you figure out the rest? If yes, then we don't have to memorize these. If no, then you should make flashcards for all of them, or do whatever you need to do for all of them. And pretty soon you can get very fast. Just look at the periodic table and you can figure out what the formula is. I call this the outer pattern. Then we have the inner pattern here. The inner pattern, I'm going to start in, what group is carbon in? What Roman numeral group? It's in group 14, but I like to use the Roman numeral. It's in group 4. Just IB. What element is that below carbon? Silicon. And so what we want to do is we want to figure out what silicate is. Silicate, how many oxygens do you think silicate has? You would think 3, but it's a new pattern. and it's 4. Silicate's 4. Do you know what the charge on silicate is? Not -3.
Just the negative.
Not negative.
Oh, so I have it right. I thought 4 originally.
Oh, did you?
And
Okay.
I second guessed myself.
It's -4. Silicate, if you're geology, yeah, silicate. Silicate, are the granitic minerals, and granite is made up of a lot of silica, quartz, whatever. Silicates are quite common, but in Chem 4 and Chem 1A, they don't really make you memorize silicate. But you should memorize silicate. And it's not that hard to memorize because you shouldn't get the number of oxygens wrong, and you shouldn't get the charge wrong. Why? Because it's a 4-4-4. Do you see 4-4-4? Group 4, 4 oxygens, -4 charge. 4-4-4. Borate is a 3-3-3. And so these are not particularly difficult to memorize. So you should be able to do that. And so if you have these memorized, these are the anchors for the patterns. And so we have the outer pattern, and then we have the inner pattern. So let's look at the inner pattern. The inner pattern is going to be different than the outer one. And so to the right of silicon is what element? Phosphorus. So we want to know what phosphate is. Phosphates occur like in detergents, although are phosphate laundry detergents banned in California? I know phosphate detergents are banned in certain states, but I think California still allows phosphate detergents. You got to worry because you get algae blooms from things like phosphate. This is a fertilizer too. I'm not sure. But what do you think? How many oxygens do you think phosphate has? How many? 4. 4 is correct. So phosphate has 4. And what do you think the charge on phosphate is? -3 or 3 minus. And so that would be phosphate. So if you remember silicate, then we can figure out what phosphate is based on the pattern. To the right of phosphorus is sulfur. So if we think about sulfate, how many oxygens do you think sulfate has? 4 is actually correct. And what do you think the charge is? -2. So this is the inner pattern here. Now, like the outer pattern, do you see how the outer pattern is extended downward in the family? Once we're here, then the inner pattern extends downward in the family. So the natural astrobiologist was thinking arsenic is feasible for life. Why? Because arsenic and phosphorus are in the same family. And so if you have ATP is adenosine triphosphate. So you have 3 phosphates in there. And so let's take a look at what phosphate looks like. I think I had it up here. We'll look at diphosphate. This is ADP. This is 2 phosphates you're looking at. ATP has 3 phosphates. Let's throw in ATP. Do you see the 3 phosphates linked together here? The PO4, the PO4, the PO4. There's other stuff in there, which maybe we'll talk about in a little bit. But that's phosphate and important for life. But we could also have arsenate. Arsenate is As. Now, how many oxygens do you think arsenate has? Yeah, excuse me, 4 is correct. And what is the charge? -3 is correct, 3 negative. And so do you see arsenate and phosphate are very similar? It's different than nitrate. There's a reason for that. We'll look at it later. It's different than nitrate. But now once we're here, we see that. And so we could have like rather than ATP triphosphate, we could have AT triarsenate, instead. Maybe that could be the fuel molecule. Like what makes ATP the fuel? It's like the gasoline for the cell, or the electric. If you're into that electric battery for the cell, you want to go electric. What makes it the fuel? It can undergo reactions. So if you have ATP, you can break off one of the phosphates and make ADP. In that process, there's some energy that gets released in that, and you can use that energy to do things. And so it should be similar. Okay, what's below sulfur? Selenium. And we want to figure out what selenate is. What is selenate? Se. Now we got to guess how many oxygens? 4. And the charge? Yeah, -2. So selenate would be that. We could go one step further from selenate. Below selenium is tellurium. And so let's look at tellurate. A lot of these, tellurate. Tellurate is probably some kind of mineral that's in Telluride, Colorado, or something like that. A little mining town. A lot of these names come from that. Borates, borax, boron, etc. So anyway, tellurate. What do you think the formula for tellurate is? TeO for charge? -2. So if we know the pattern, we could do more, So for example, if I asked you what germinate is, and germinate is Ge, what would you say? You'd find where Ge is on the periodic table, and then where's Ge? Ge is right below silicon. So if I asked you what germinate is, what would you say? GeO4 4-. So that's the power of patterns. Power versus just straight memorization. If you did straight memorization, you'd say, I didn't make a flashcard for germinate, so I don't know what germinate is, right? And so you'd never be able to answer that. Or it wasn't on our list. Like most of these, a lot of these aren't on our list. But if we know the pattern, we can figure it out. That works great if there's a pattern, but sometimes there isn't a pattern. So this is the pattern on the periodic table. Unfortunately, now we got to make flashcards for the 8s that aren't in this pattern. So do we have any 8s that aren't inside this pattern? And the answer is yes, but some of these 8s that aren't inside, we could still use patterns to figure out. And so what 8s aren't inside the pattern? Take a look at. The first ones I want to talk about are things like perchlorate or bisulfate or hydrogen sulfate, etc. Okay, and some other stuff. So we're going to continue on with this periodic pattern right now until we can't. Okay, so we're looking at other numbers of oxygen, and so we'll have a series here. with same charge. And so what do I mean by series? The series is going to look like this. We'll have something called the per 8. And then we'll have the 8. And then we'll have something called the ite. And then we'll have the hypoite. So what we do with this is the 8 is our reference point. And so the 8 we get off the periodic table. The per 8 is plus 1 oxygen. So an example of this would be chlorate. If we do chlorate, which will be our reference, is chlorate in the 3 oxygen or the 4 oxygen block? 3 oxygen. And what is the charge on chlorate? -2? -1, or just minus. Okay, so our reference is chlorate. So this is chlorate. And now we want to figure out what is perchlorate. Perchlorate is plus 1 oxygen. So if we start off with 3 and add 1, we're going to be at 4. And the charge doesn't change, so it's going to be the same negative charge here. And so this would be perchlorate, 1 more oxygen than chlorate. All right, what if we have 1 less oxygen? Then we go from 3 to 2 oxygens. And this would be the same charge, and we call this not chlorate, we call this chlorite. And then that's -1 oxygen from the reference. That would be the ite. The hypoite would be -2 oxygens from the reference. And so if we start off with chlorate and go to hypoite, then we lose 2. Or if we start off with chlorite and go to hypochlorite, we lose 1. And so we're at 1 oxygen. We don't write the number 1 as a subscript or on the charge. So this is just ClO minus, and this is called hypochlorite. Hypochlorite is bleach. Bleach is what we call a good oxidizer. You know, people use bleach to do different things. Including water. You know, they're talking about, when I was in Boy Scouts, we either carried chlorine tablets. You know, chlorine is what number on that chart from the bottom right? F2, do you see that? What number would chlorine be? No, I'm sorry, on the left chart. Probably chlorine is what we call a diatomic element, so it's a little bit confusing. It's Cl2. You know what? F2 is called fluorine, and then hydrogen peroxide. Do you know what MnO4 minus is called? It's called permanganate. We'll learn that one in a minute. And this is chlorine. So chlorine is number 4. These are all oxidizers. And so chlorine is a very powerful oxidizer. Chlorine is more powerful than oxygen. Oxygen is more oxidizer than main oxidizer. And because main oxidizer, you have a fuel, you need an oxidizer. So oxygen is the most common oxidizer because it's free. You have to pay for using the oxygen in this room to burn your natural gas. You don't have to pay for that. You have to pay for the natural gas, but fortunately you don't have to pay for the oxygen yet. Maybe there'll be a tax on oxygen in the future, but right now there's no tax on the oxygen. And so anyway, getting back to this, Hypochlorite, we used to carry chlorine tablets. The chlorine tablets were just solid bleach, or we carry bottled bleach. What do we use the bleach for? Use the bleach to kill microbes in water, and then you can drink it. And so I'm used to the taste of bleach. Not at high concentrations. Of course, at high concentrations, drinking bleach is going to kill you, but at low concentrations, you did it. And then growing up, I grew up in
Some dirt in your ear.
I grew up in Santa Barbara. In Santa Barbara, they treated the drinking water, the tap water, with chlorine, and so all the water tasted like chlorine. So it's kind of used to it already, and so it wasn't too terrible. Now I don't think I could drink water with bleach in it. It just tastes awful. No, I drink filtered water or this. It tastes much better. But as a kid, I drank lots of that. Especially if you go like in the backcountry here, all the water's stagnant. There's all kinds of stuff growing in it, algae, whatever else. Gonna kill that stuff before you drink it. On like backpacking trips. But now we have filters. These filters. We used to just put the water in a bottle and shake it up with bleach and then drink that. It was awful. It turns out that these are even more powerful than bleach, but we'll talk about that more later. These are more powerful because, if you think about chlorine, what is the charge range on chlorine? Because look at the position on chlorine, and chlorine can range from what? If it gains, it goes negative. If it loses, it goes positive. So if we look at chlorine, how many can it gain? How many can it lose? So let's take a look. Maybe we'll go to the fancy periodic table here. Here's chlorine. So we use these numbers sometimes to help us. So if we go from 17 to 18, then we're there, right? That means we go from this means we go from this is the number of electrons and the number of neutrons. Protons. We'll talk about this later. But we can gain one electron, so that gives us our -1. How many can we lose? We can lose 7. If we lose 7, then we're at 10. Then we're good. Does chlorine like to lose? No, isn't it much better if chlorine gains? If chlorine loses, yeah, it wouldn't be so happy, and it's got to lose a lot in order to get here. And so I'm going to talk a little bit because there is some theory involved with this that can help you remember this stuff. Historically, the 8s are associated with, is that mine? With maximum oxidation state. And so this is one additional way of remembering these types of things that helps to lower the amount of memorization. Perchlorates at the top. Actually, the 8s and the perchlorates at the top. The 8s, traditionally in geology, these things have been completely oxidized. We live in an oxidizing atmosphere. If you study geology, the atmosphere has changed. At one time it was what we call a reducing atmosphere, and then it changed to an oxidizing atmosphere. And you can see that in geologic history. Well, we live in an oxidizing atmosphere, and so what that does is oxidizes everything. And normally when we think about the max we can oxidize is the 8s. So this is why it's so common, when people go look for minerals or go look for compounds, most of the compounds are 8s. They're 8s because they've been totally oxidized from the oxygen in the air. But sometimes it goes a little bit beyond that. And so chlorate would be more common, but it turns out it didn't quite go all the way. And the way we can figure this out is something like this. Oxygen has a long history of taking electrons. And oxidizers take electrons, so that's why oxidizers are named in in honor of oxygen, because oxygen wants to take how many electrons? 2? Can you tell by looking at the periodic table how many electrons oxygen wants to take? Well, it's at 8, and it wants to get to 10. How many electrons is it going to take? 2. In fact, the whole oxygen family takes 2. So if each oxygen takes 2, then it has 2 extra electrons, and we get 2 minus. And so I have 4 of those. And so if I look at the net negative charge, this minus 2 times 4 is going to give us minus 8. And then I have 1 chlorine at plus x. And so minus 8 plus x has got to equal minus 1, the overall charge. So what is x? Plus 7. And so we call x Roman numeral 7. So this is chlorine 7. Chlorine 7 is not happy. But anyway, that's chlorine 7. Let's look at hypochlorite. If we go to hypochlorite, on the other hand, hypochlorite is oxygen likes to be minus 2, and then that means chlorine's got to be plus what? We'll call it plus x to equal minus 1. Chlorine is plus 1, so we'll just call that Roman numeral 1. And so in bleach, chlorine is plus 1. In perchlorate, chlorine is plus 6. And so, in other words, chlorine doesn't like to lose anything. Chlorine likes to gain. Chlorine, you know what chlorine's preferred charge is? Chlorine would be very happy at minus. Look at the periodic table. Tell me what the charge on chlorine should be. It should be minus 1. Chlorine should be minus 1. If it's plus 1, it's lost 2 electrons. It's not so happy. So bleach is a good oxidizer. Oxidizers try to take electrons. And so bleach is an excellent oxidizing agent. This is why you use it to bleach the water, to kill all the microbes in there. And then, well, you don't have to use bleach. You could use other things too. You know, other things work at oxidizing microbes as well. Do you know what a common oxidizer that's used to oxidize microbes is? Maybe not as hard as chlorine. Chlorine's kind of harsh. Chlorine is 0. Bleach is plus 1. You know, the charge on chlorine is 0. The 2 will be no charge. The chlorine's a pretty good oxidizer. Bleach is a better oxidizer. But it's this one. What's this one? Iodine. So iodine's a pretty good oxidizer that's used. So there are certain countries like what was it like you know they didn't have enough doses for the vaccine like in certain countries and they couldn't give it to all the citizens of the country. So you know what they told them to do instead was to do aspiration. And they have a solution called povidone iodine. Have you heard of it? Povidone iodine. This is an iodine solution. And so they take the iodine solution, and then this. I've been doing this myself too. So if I feel some congestion coming on, or I feel like I'm some sore throat coming on, what I'll do is I'll gargle with some iodine solution that kills some of the microbes there, and then I'll do a nasal aspiration with iodine. It's a diluted iodine. I don't use the povidone iodine. I just get the povidone iodine at the pharmacy. It's just over the counter, and you're just bleaching out. And apparently, it's very effective. You know, people don't get sick that way. So if you're prone to catching bugs, you might think about doing that. So nasal aspiration. And so all it is if you've gone swimming and you've gotten a whole bunch of chlorine water in your nose. Have you ever felt that? in the swimming pool, it feels just like that. In fact, it brings back memories. Each time I do that, it brings back memories of going swimming in a heavily chlorinated swimming pool. It feels just like that, And it's iodine, and iodine's different than chlorine, but the taste and everything else is the same. It's kind of interesting. I don't know if you want to do that, but I've been doing that myself. And you can read about this if you're interested. But it's an oxidizer, and we're interested in those. All right, so these are other things to help you remember. So could there be a perchlorate? Do you think there could be a perchlorate where we just add another oxygen? No, but some things are already maxed out. So for example, chromate is already maxed out. Let me just do a sidebar here. Is there such thing as perchromate? Well, not in this sense, there isn't. There could be something of a perchromate, but if we have 4 oxygens here, that's the max. We cannot go to 5 oxygens, because if we have 4 oxygens here, it's going to be O2 minus, O2 minus, O2 minus, O2 minus. That gives us a total minus charge of -8. And then we have 1 chromium. We have 1 chromium, and the whole thing has to add up to -2. So chromium's got to be plus X. What is X? -8 plus X is equal to -2. Chromium's got to be plus 6. Chromium's plus 6. So what's the range of charge for chromium? Plus 6. Plus 6 is what we call the max. Plus 2 and plus 3 are much more common. So this is a plus 2, plus 3. But plus 6 is the max. It's in group 6. And so chromate, there's no perchromate like there is perchlorate. There could be because might be a peroxide. And so we might have 2 chromates joined together by a peroxide. But we'll talk about that in a minute. Let's see what time do we start. 1:15. Oh, I went too long. Let's take a break now, and we'll start again. Sure. Sorry, I just forgot to record it, so there's going to be a gap, a little bit of a gap there in the recording. Phosphate forms phosphoric acid. Sulfate forms. Is that sulfate? No, that's not sulfate. Let's skip that. Carbonate forms. This is what? Nitrate forms. Acetate forms. Acetic acid. Oxalate forms. Oxalic acid. Acetic acid you can eat. Oxalic acid, don't eat that. It'll cause like kidney stones. Perchlorate forms. Chlorate forms. Okay. And then that's all the 8s that we have. But what if it's not an 8? What if it's an ite? And so what do we do in that case? So let's talk about that next. So the first pattern is that the 8s form ic acids. Okay, what if we have an ite? What does an ite form? An ite will form an Aus acid. Carbonite is not common, so do something else. Let's do, you know what nitrate is? What is nitrate? NO3 minus. So what is nitrite? NO2 charge minus. So if we look at nitrite, NO2 minus, then the acid would be adding enough H pluses to neutralize the charge. So we only need one H plus to form HNO2. So nitrite will form what acid? Nitrous acid. So that's the other pattern. So let's take a look at this. Let's look for some ites. We don't have that many ites. Here, nitrate has 3 oxygens. Nitrite has 2 oxygens. So this is nitrous acid. Here we have chlorate forms chloric acid. Chlorite forms chlorous acid. And this would be hypochlorite. Hypochlorite forms hypochlorous acid. That's it. Okay, and then finally, we have one other type of anion, and that's the anion that ends in D, IDE, ides. For ide, we add the hypo prefix and the ic acid suffix. So a common ide would be chloride, and we need enough H's to balance the charge, so we'll form HCl. And the name of this gets changed. So we go from chloride to hydrochloric acid. Oops. Here. So the ides get changed to hydro. Let me fix that. Oops. Okay, and let's take a look at our chart. F minus is called fluoride, and that gets changed to hydrochloric acid. Chloride gets changed to hydrochloric acid. Bromide gets changed to hydrobromic acid. And iodate gets changed to hydroiodic acid. One of these acids is the strongest of the 7 common strong acids. Do you know which one it is? So let's take a look at this chart over here. This chart is the acid ranking chart. Can you name this acid at the top of the chart? Well, first we got to recognize the anion name, ClO4 minus. What is ClO4 minus? Perchlorate. And so that would be called perchloric acid. It's because the A ending, the I gets the hydro, only with the ides. And it doesn't matter if it's monatomic or polyatomic. So for example, HCN is cyanide. And so it would be changed to hydrocyanic acid. So HCN is called hydrocyanic acid. There are things you could do with the names. So some people, they imagine water as being, with nomenclature, there are different ways you can name things. So if we imagine water as being H plus and OH minus, this is just a side topic here, but if we imagine H plus and OH minus, how would you name that? So this is hydroxide. And so what do you do? Hydrohydroic acid. And so would you want to drink hydrohydroic acid? No. And if you probably can convince people, and you probably can convince people in government to ban it, hydrohydric acid, right? And so somebody pulled a prank to the city in Orange County, getting them to ban things like hydroic acid, aka there's another name for water. It's called dihydrogen monoxide. Would you want to consume dihydrogen monoxide? So these pranksters convinced the city through meetings to issue a ban of dihydrogen monoxide in the city, and then they got a kick out of that or something. It didn't actually go through because somebody found out that dihydrogen monoxide is water. And so there are different ways you can name these things, just following the rules. So dihydrogen monoxide ban, and I think it was like multiple bans. Change.org. They call it DHMO, ban DHMO, and these are just seeing how many people they can trick into banning DHMO. And they were successful for a number of people. Maybe the UK Parliament did it too. Dihydrogen monoxide is used as an additive in the vast majority of food and drink products out on the market. We call upon the government to regulate this. Yeah, that's a sense of humor, but it's funny. All right, so that's to try to minimize the amount of memorization, but unfortunately, you're still going to have to memorize stuff because not all the eights occur on the periodic table. So which eights do not occur on the periodic table? How late do we go till? Okay, so we have time. For example, acetate. Is acetate on a pattern in the periodic table? Unfortunately not. So acetate, you're going to have to make flashcards or write it over and over again. And the way I memorized acetate, let me tell you. Is 2321. C2H3O2 minus 1. So I just, I had this thing, I just said 2321, 2321, and then I was able to figure it out for the test. But you could do whatever you want, whatever works, but unfortunately you'll have to memorize this one too. Acetate. Now the thing about acetate is this is one way it's written. There's another way that acetate's written. The other way that acetate's written is like this. CH3COO minus. So these are two common ways that we write acetate. The reason they write it like this is because it tells us more information about the structure. So acetate makes what acid? We don't have to memorize this because we can figure it out. If I wanted to make this into an acid, I needed to add enough H pluses to cancel out the negative charge. So how many H's do I need to add to acetate? Actually, just one. And so I can form the acid based on acetate. What do I call this acid? Yeah, acetate gets converted into acetic acid. Acetic acid you can buy in the supermarket. Do you know what they call it? Some people eat this stuff. They call it vinegar. Acetic acid is vinegar. And so this is acetic acid. And the reason they write it like this or they write it like this, CH3COOH, is to tell you how the hydrogens are bonded. So when we look at this, this tells us these hydrogens are different. This one tells us these hydrogens are different. These three hydrogens are bonded to this carbon. This hydrogen is bonded to the oxygen. So we have four hydrogens, but they're not all the same. Three of them are kind of similar, and the fourth one is different. And so the hydrogens are different. And so this is why it's written like this. It's written like this so it's easier to tell the difference between the hydrogens. Sometimes on the nomenclature exam, I give it and I see this. I see them write it C2H4O2. And I wonder, why are they writing acetic acid as C2H4O2? And then I know why they're writing it as C2H4O2. Because that's what Wikipedia says acetic acid is. Acetic acid is C2H4O2, but we're losing structural information. And so the second formula is called the structural formula. So look for acetic acid on the chart up there. Can you find acetic acid on the chart up there? Let me narrow it down. It's on the right side of the chart. Do you see it? Where is it? It's the second one from the top. Here's acetic acid, and do you know what that is? Acetate. And so they're using the structural formula here, so we have to actually know both. But for right now, just work on the 232, the simpler one. And so let me highlight that. The structural formula you'll learn more about later. Here. This formula is not used. This formula leads to confusion. Does this look like an acid to you? No, acids usually begin with H. And so this one I wouldn't recommend memorizing here or using. Okay, what else do you have to memorize outright? So we have acetate, we have chromate. Chromate is not on the chart, and we have dichromate, which is also not off the periodic table. So let's add that to our list of things to memorize here. Chromate is CrO4 2-. And we have one other chromate. It's dichromate, Cr2O7 2-. Chromate and dichromate were contaminating the water in Hinckley. This is what was causing the cancer cluster there. Both of these are chromium-6 ions. This is a 2 here. That's a 7 here on the ends. Now, dichromate, di means what? 2. So it should be 2 chromates. So one of the questions that comes up is, why isn't it Cr2O8? What happened to the one missing oxygen? Do you see an oxygen's missing? And what happens to the missing oxygen is this. We don't like to form peroxide linkages. And so if we have a chromium here, if we retain all 8 oxygens, then we form a peroxide bond. A peroxide bond is this oxygen-oxygen link right here. And peroxide bonds are unstable, like in hydrogen peroxide. Hydrogen peroxide has a peroxide link like this. To make this more stable, what we do is we lose one of the oxygens. And so in dichromate, we link it like this. So we lost one of the oxygens. We total up the oxygens now. We got 1, 2, 3, 4, 5, 6, 7. Do you see that? And so the reason we lose one of the oxygens is to prevent peroxide linkages. Peroxide linkages are inherently unstable. If we look at ADP, which I had up here earlier, what is phosphate? Phosphate is PO4, right? But take a look at this diphosphate. Diphosphate should be 2 phosphoruses, P2, and how many oxygens? It should be 8 oxygens because each phosphate. How many oxygens do I have here? 7. Why do I have 7? It should be 8. Because I got to lose one in order to prevent linking them by a peroxide link. It would be inherently unstable. And so ADP, and the same thing happens with ATP. You know, it's not doubled because of that peroxide bond. We want to prevent that. The next thing that's confusing is the charge. Shouldn't it be double the charge? If I have 2 chromates, I should go to -4 or 4-, right? But it doesn't because of the way the electrons are arranged here in the structure. I'm not going to talk about it now, but it's the same charge. So dichromate is almost 2 chromates, -1 oxygen, but the same charge here.
Why? Is it just because of the structure?
Yeah, it's because of how the electrons get rearranged in this particular structure. It just still comes out to a -2 because of the way it's linked together. So we have to memorize that. What else do we have to memorize? There are 10 of them that we outright have to memorize. What are the 10? We got borate, remember that? Silicate, cyanide, hydroxide, peroxide, acetate, chromate, dichromate. How many is that? 6, 7, 8. So we got 8 out of the 10. What are the 2 remaining ones that we have to outright memorize? So dichromate, we already did cyanide, we did hydroxide, we did peroxide. We have to do oxalate. So oxalate is C2O4 2-. C2O4 2-. This will be oxalate. Oxalate, the structural formula is OOCCOO, and there's a negative and a negative on each end. And so we could say that, or this. Oxalate's on the chart on the right side of the chart, top right. There's oxalate ion. And it forms an acid. Do you know what the acid name is? Oxalic acid. And how many hydrogens does oxalic acid have? 2. Oxalic acid is on the left side of the chart, middle, and the name oxalic acid is written there. And so this is oxalate. Oxalate will have to... and so people eat acetic acid, but people won't eat oxalic acid. It would be poisonous. All right, that's oxalic. And then we'll go down. Permanganate is the next one. Permanganate is MnO4. And the charge is tricky here. The charge is very tricky, but there's a way to remember the charge. When you see per8, what do you know about the oxygens? The oxygens are totally maxed out. And so if you see per8, actually the oxygens can be maxed out either with an 8 or per8. The per8's kind of this after the fact, and when they realized the 8 wasn't enough. And so when you look at this, the one way to remember the charge is by doing what we did earlier. Each oxygen is -2 because oxygen wants to gain. Oxygen is the namesake of oxidizer, and so it gains electrons, and it's going to gain 2 electrons. So we have 4 of those. This is going to give us a -8 total. And then we only have 1 manganese, so this is plus X. Plus X plus a minus X, 8 is equal to -1. So what does X have to be? 7. And so it's maxed out. What is the Roman numeral group of manganese is in? 7. It's in group 7. So if you remember manganese is 7, oxygens are -2, then the charge on permanganate is -1. And so that's one way you can remember it on a semi-theoretical basis. But otherwise, people get this charge wrong all the time. A lot of people write -2 for the charge. It's incorrect here. And so what does that make it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 10 we have to memorize whatever way you can memorize it, and however you want to memorize. The rest, everything else we can get from the pattern. And so you have a choice. You can memorize these 10 and understand the pattern, or you can just memorize all of them, plus some. Okay. And so people always ask me for a list of ions to memorize. Well, it depends. Can you do the pattern? If you can't do the pattern, then you can start off with a list here and then add some, like borate, silicate, etc. Just make some additional flashcards. Or memorize these 10 and then know the pattern. Okay, that's what you need for memorization. And so this thing I'll post on Canvas. Okay, are there any questions with this? I'm sorry? What? Yes, it's a lot to take in. So the sooner you start taking it in, the easier it'll be, But the problem is, not only do you have to memorize this, but, there's more stuff we got to memorize. The more stuff we got to memorize are things like the solubility rules. The solubility rules always kill students because there are only 7 solubility rules that they actually 8 that they have to memorize, but everything starts becoming overwhelming. Permanganate. And et cetera, et cetera. So this, the nomenclature. Do you know what chapter nomenclature is in? Chapter 6. Nomenclature is in chapter 6. So why am I jumping so far ahead? Because if I cover it in chapter 6 and then I test you on exam 2, most people don't do very well. But if I cover it now and then by the time exam 2 comes, they're okay. I think this will be on exam 2, not exam 1. I'll have to look again. Maybe it's exam 1. But the thing is, how do you memorize? Memorization is a lot of work, but there are ways to minimize the amount of work that you do. Like, you memorize the path, like going to elementary school or going to middle school or going to high school, you might have memorized the path to get to school, right? But if you do that so many times, it just becomes ingrained. Let's say you move to a new school and the first time or you go, it's kind of confusing, but the 100th time you go, do you even have to think about it? No. And so that's the way I do when I study. This is the way I study. Is and somebody asked me this morning, so I'll just mention it today here. I try to write down as much. I don't read the chapter before coming to class. If I read the chapter before coming to class, maybe I'd understand a lot more of the lecture or understand a lot more of the presentation. But I don't really care if I understand it or not. What I try to do is I try to just write down everything I can. And there are going to be things that I don't understand, but those things that I don't understand, I try to figure out what those are. So immediately after class, let's say at UCLA, immediately after lecture, what I do is I go to, let's say, Kirchhoff Coffee Shop, which is really noisy. It has a lot of white noise. And then I'd read through my lecture notes. And then I'd make a note of things that I don't really understand, the things that were confusing. Okay, and then I'd focus my reading on those. So then after I go through my notes and write little annotations here and there, I'd start the reading. And the reading, I'd really zero in on the stuff that was confusing. And the stuff that made sense, I'd just skim through. I really wouldn't read it in depth. Okay, and oftentimes that worked because then I can annotate my notes afterwards. And sometimes, sometimes I can't write fast enough. In high school, one of my teachers said, learn shorthand. If you do shorthand, you'll get A's in all your classes because then you can write down everything they say. Well, I wasn't fast enough, so I would bring a recorder, but most of the professors there didn't allow a recorder. There was, I think, there's one class that allowed a recorder. It was history of French film. And so I was able to record all the lectures. And then that class was an easy A because I didn't miss anything. And then I had everything like memorized. And it's not just memorization, but it's easy to memorize. I didn't go in with the purpose of memorizing things. What I would do is I'd just make sure my notes were complete. And if there was something I didn't understand, I'd make sure I understand that. And that included the calculations. So if they did calculations in class, I'd repeat the calculations and make sure I could do those on my own. And I'd make sure each step of the calculation I understood. And sometimes, the calculation appears easy because the professor is doing the calculation on the board and it looks simple. But when you sit down and actually do the calculation yourself, then you go, should I go this way or should I go that way? It becomes confusing. And the way I think about it is like, let's say you're going, you're a tourist in the jungle and you have a guide. And the guide walks you through the jungle, and you just follow the guide, and the guide makes it look easy because you get from here to there without any problem. And so the next day you go, okay, I don't need a guide because it was so easy. But then when you're in the jungle by yourself, then all of a sudden you notice certain things you didn't notice before. You notice there's a fork, and you're trying to remember which way did the guide go? Did the guide take the left fork or the right fork? And you can't remember, but you never thought of it because you're just following the guide. And the same thing happens with these calculations. All of a sudden you come to a fork. Do you take the left fork or the right fork? Which way do you go? And then all of a sudden it makes it much harder than what it appeared. So to avoid that from happening, I would go through the calculations. And a funny story came up. When I was a graduate student at UCSB, one of the professors was actually a good friend of mine, but he was telling me about his grad class. He's a theoretical chemist. He was teaching a quantum class, and he went through a calculation which took 4 lectures to complete. This class only had 6 students. And so after he finished the calculation, he asked, any questions? Do you all understand it? And everybody said, yeah, it seemed pretty straightforward, because he did all the calculations on the board. Everybody was able to follow along. Since everybody was able to follow along, he decided the next lecture, he would test them on it. So it was like a surprise test. So he gave a pop test. And do you know how many people repeated? You think everybody could repeat it because all they had to do was repeat the exact same calculation that he just finished doing on the board, so it was fresh in their mind. But do you know how many people actually was able to repeat that calculation? Only 1 out of the 6 students was able to repeat the calculation. And that means 5 couldn't finish it. And these are all chemistry PhD students. So you'd think they're pretty serious, but it's like one of those things. When you watch somebody do it, it's different than doing it yourself. And so I'd do all the calculations, I'd make sure the notes were complete, and I'd make sure I understood everything. And sometimes this involved me going to the bookstore. I'd go to the UCLA bookstore when they had all the books there, and I'd look for more advanced books. More advanced books, in my book, it might cover it in 1 paragraph. In a more advanced book, there might be a whole chapter dedicated to it. And so if I didn't understand that, I'd look for more advanced books to try to get more in depth. into the topic so I could better understand it. If that didn't work, I'd go to the TA. The TA is the teaching assistant. If that didn't work, I'd go to the professor. And I do this pretty soon. I do it early. I wouldn't do this the night before the test, because I used to do it the night before the test, but it would be too much memorization, too overwhelming to try to cram everything the night before the test. Okay, once I had the notes complete, then every day I read my notes from page 1 to the last page. Every day I read it. And so if you read your notes every day, then by the 10th week, you already have it memorized. I had maybe 60, 100 pages of notes. I had everything memorized by the test. But, I didn't go in with the purpose of memorizing. It just happened. It happened because you see it every day. When you see it every day, it's a lot easier to remember. And then you have it down for the test. So the memorization may seem overwhelming, but it depends on how you spread it out. If you spread it out like that, there's no work involved. I didn't have to work. I used to have to work with the flashcards and with writing, but I changed. I switched it to this. And so this is why I'm covering it now, so you can look at it every day. You look at it every day. It's simple. It's not difficult. It's only 10 ions. How hard is that? Plus some rules. It shouldn't be too hard. But still, it's hard, and still lots of people fail nomenclature. And so anyway, just try it. Whatever way works for you is the best way. And you should do it. Sometimes it takes some time to figure it out. For me, it took some time to figure it out. Okay, let me continue. With this. All right, so you want to get started with that memorization, and now we're going to talk about matter and energy. We're just going to continue this. So what we want a little bit more insight. Why do you want to write acetic acid CH3COOH rather than HC2H3O2? Because by writing it CH3COOH, we get more insight into its structure. And we want to know composition, structure, because by knowing composition and structure, we might be able to correlate it, or we might be able to figure out its properties. And what we're most interested in are the properties of matter. And so we talked about this. Where did we leave off? We talked about this. I mean, this is what, if we write this CH4, we got to think, what is the structure of that? And later on, we'll look at the theory a bit more, and then we can figure out it occurs as this type of structure. This type of structure is special. This type of structure has what we call spherical symmetry. It's like a ball. And so if you were to stick this inside a ball, it's totally balanced. If you want to balance this. And that's what we call spherical symmetry. This would be perfectly balanced inside a sphere, as best as it could be. And this angle is what we call the tetrahedral angle, and the structure is called the tetrahedral. And so that gives us some clues about how this might vibrate. The way methane vibrates is different than the way water vibrates. Water is what we call bent structurally, and it only has 3 vibrational modes, whereas methane can vibrate in different manners. Actually, we might as well take a look at how these are determined from quantum mechanics. Like, for example, water only has 3 vibrational modes. Each of those vibrations corresponds to a specific energy. So it takes a certain amount of energy to vibrate water like this, a certain amount of energy to vibrate water like this, and a certain amount of energy to vibrate water like this. Those are 3 specific energies. So if you heat a pot of water on a stove, the stove flame provides a spectrum of energies, and most of that energy is wasted. most of it's wasted because you can't vibrate water with those energies. You can't rotate the water with those energies. There's certain energies that do it. And so this is the brilliance of the microwave oven. The microwave oven pinpoints the energy. The microwave oven doesn't vibrate water. The microwave oven, do you know what it does? The microwave oven is tuned to the energy of rotating the water molecule. And so if you pinpoint that then and not blasting it with a whole bunch of different energies, you're not wasting as much energy. So you can heat up water much more efficiently with like a microwave oven than with other things like an infrared lamp or whatever else. So, boiling. It's the same thing. Heating up and boiling, you're trying to do or accomplish the same thing. Let me see if this is still on. Yeah. So let's take a look at some of the vibrations. I talked about Aaron Brockovich and Bhopal, but I didn't talk about the molecular dynamics simulation. Okay, so we're going to look at this. So we want to understand things based, properties. We have gas. Gases have certain properties. All gases have certain properties. One of the properties is that they're compressible. Another property is that they fill to or expand to fill the volume of the container and whatnot. And so what about the structure of a gas lends it that property? And then we have liquids. And liquids will have different properties, and then we have solids which have different properties. And we try to understand these based on the structure and composition of what they're made out of. And so let's take a look at this molecular dynamics simulation here. This comes from quantum mechanics here. And what we're looking at here is ice. Have you ever seen like a snowflake crystal? Or a single crystal of ice? They result in a really pretty pattern. And the really pretty pattern results from how the water molecules are arranged in the solid. Because in a solid, what types of motion are there? And the types of motion are, what types of kinetic energy are there? Because kinetic energy is motion, the energy of motion. And so what kinds of motion can we have? Vibrational. And so solids, these can be vibrating. The three vibrational modes from quantum mechanics. What else can they do? Rotational. But these are kind of stuck. They're really stuck together, so they can't rotate. In some solids, they're able to rotate, but not in ice. And what are the types of motion? Translational. There's no translational motion here. So the only motion in solid ice is vibrational. And the water molecules are arranged very orderly. Do you see that? We call this an ice crystal. In the ice crystal, there are these channels here that are empty, and it's not very dense. There's kind of empty space there. So let's take a look. This is the scale here. Do you see the scale? Do you know what A stands for? A stands for angstroms. Okay, do you see the vibrations? Okay, now what's happening here? It's getting hotter and hotter, and so now the ice just melted. Do you see that? And now we have liquid water. Let me back it up a little bit. Do you see liquid water? One of the things, and this is a physical property, is that liquid water is more dense or less dense than solid. It's more dense. And that means ice floats on top of water. If ice didn't float on top of water, then we wouldn't have life, they're saying, on Earth. And so when you take biochemistry, chapter 1, biology, they talk about ice. One of the properties of water that support at least marine life is density. Density is a solid, density is a liquid. All right. This doesn't expand. The molecules here are all in contact and they're stuck to one another. But now we have rotational motion and translational motion that you can see in the simulation. Let's see. It's hard to see. There's some rotational and translational motion. And what happens if we keep heating it up? Yeah, you're gonna have more translation. We're gonna have more energy, and you see it's gonna break apart. They're kind of sticky. They're stuck together, and then we heat it. Now this is gaseous water. Gaseous water has these large gaps. Gases, since they have this empty space, are compressible, and gases will fill the volume because they have enough kinetic energy to expand to fill the volume. That would be a molecular dynamics simulation. So based on the structure of methane has a different structure. It has that tetrahedral structure. So the vibrations of tetrahedral are different. And so when we look at the vibrational modes of methane, these are the ways methane can vibrate based on its structure. And these are the energies of vibration. The vibrations here occur in the infrared region. And that's where most vibrations occur, in the infrared region. Did I talk about the spectrum? Didn't, right. Light interacting with matter. We have different energies, and so there's additional memorization you have to do. One of the things we memorize are the colors of the rainbow. Do you know the colors of the rainbow? Mm-hmm. And so if we have white light here, white light contains all colors, and the colors that we usually refer to are Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. But we take it one step further. When we characterize it, we like to characterize it either by its energy. You know, red light's low energy, violet light's high energy. So if you're working in a dark room, it's red light. You know, red light because low energy, less to expose the film. But the cutoff there, and we usually use something called wavelength. And the wavelength there is for red is 760, and at violet it's 390. And why do we want to memorize those? So then we might be able to guess like green. If we know the extremes, so I memorize red, 760, that's the beginning of red, and I memorize the end of violet, 390, then that goes from about 800 to 400. And so right in the middle is green, so green should be about 600, right in the middle of that range. So if we memorize some of the extremes, then we can kind of figure out what's in the middle. Now, if we're past in red, you know, going past red, what we are in, we're in infrared. And so if I'm at 1,000 nanometers or 2,000 nanometers, that's not invisible, that's past red. And so that must be infrared. 1,000 nanometers is called a micron. So infrared is typically in terms of microns. And so we can measure these vibrations in microns, or infrared spectroscopists use these ones. These are called wave numbers, and these are related to energy. But these vibrations occur in the micron, and so sometimes you'll hear about micron wavelengths. Whereas on the opposite side of violet, the violet ends at 390. So let's say I'm exposed to 200 nanometer radiation. If I get exposed to 200 nanometer radiation, that's beyond violet. Do you know what's beyond violet? Ultraviolet. And I don't want to be exposed to 200 nanometer radiation. I want to protect myself from that. So by memorizing 2 points, we can kind of figure out other points in the spectrum. So there is a bit of memorization, but we try to minimize the amount of memorization by looking at patterns. And those would be the patterns of light, and light can do different things. Infrared light can cause vibrations. So micrometer wavelengths cause vibrations like this to occur. And methane has a lot more vibrations than water. If we look at the vibrations, just the vibrations alone of water, we can look at that here. Vibrational mode of water. A lot of people, water's so common. So one of the vibrations. that corresponds to a different energy. This is just cartoonish here. Those are the three vibrations. They give names to these vibrations here. And you can see this on the spectrum. Let's see if we can see it more. These are the names they give them: symmetric stretch, bending, asymmetric stretch. These are the energies. So when we look at the energy, see, beyond red is infrared, and so these occur in the infrared, and these are 1,000 nanometers is 1 micron. So this goes from 1 micron up to 10 microns, and we see these are bands. This is the visible here. This is the ultraviolet over here, and this is where these occur in the spectrum, light spectrum. So we're interested in how light and matter interact, for whatever, for boiling water, for doing whatever. We want to know how those interact. We talked about physical properties and we might modify this a little bit. Characteristics that can be observed and measured without altering the identity of the substance. And chemical changes, chemical identity of the substance is destroyed and a new substance forms. And so when we're doing that, matter gets rearranged. And when we're talking about matter getting rearranged, not rearranged, rearranged. And for physical property like boiling, it does get rearranged, but not in the sense of the chemical identity. So when we look at liquid water, it's still water molecules, but now they're spread apart. Here, they're water molecules. And so the chemical identity, that is, the atoms aren't rearranged here. So the same thing, when we melt ice and make water, we still have water molecules. Whereas in the chemical change, the atoms get rearranged. And so we're going to start talking about the rearrangement of atoms. So let me tell you another thing you have to memorize, and that is the metric prefixes. Do you know the metric prefixes? So let me write those down. But I'm fortunately running out of time here. Capital M refers to mega. And mega is a million, like a megabyte. We're not going to go beyond, like, what's bigger than a mega, like a megabyte? A gigabyte, terabyte, etc. We're not going to go that way because chemists don't usually do that. But if you're a computer person, you want like a gigahertz, not a megahertz, let's say, processor, something like that. But for us, this would be about it. Maybe we would go gigahertz or something. And then K would be kilo, which would be 1,000. And then M, or actually C, we'll go to C. C is a centi, which is 1/100. And then we go to M, which is milli, which is 1/1000, or 10 to the minus 3. And then what's smaller than a mu, which is micro, which is 10 to the minus 6, 1/1 million. What's smaller than micro? Nano. How big are atoms? Are they micrometers? They're pico? Yeah, they're hundreds of picos. So nano would be 10 to the minus 9, and then we would go to pico, which is 1/1 billionth. And so atoms range in size from about what to what? How many picometers to? Not 1 to 6. It would be too small. Too small. Atoms range in size from 100 to 600 picometers. So why do they use that? There's another unit that's used, and that atoms range in size from 1 angstrom to 6 angstroms. And yeah, you're thinking angstroms. But the reason why picometers is preferred is so we can get rid of the decimal point. Did I talk about that yesterday? So rather than saying 1.5 angstroms, you just say 150 picometers. And then we get rid of the decimal. And so angstroms or picometers are used for atoms. But we're going to go even smaller. What's smaller than pico? Femto, 10 to the minus 15. What's smaller than femto? Atto, 10 to the minus 18. So why do we care about atto? Why do we even care about these small ones? Let's say in in a microsecond. How long is a microsecond? A microsecond is very quick, isn't it? Because if you take 1 second, you'd have 1 million microseconds in 1 second. Could you count from 1 to 1 million in 1 second? No. And so why do we need something that fast? How about a nanosecond? Well, that would involve counting from 1 to 1 billion in 1 second. Could you count to 1 billion in a second? No. Could a machine count to 1 billion in a second? Is there a machine that's fast enough to count to 1 billion in 1 second? How about a pico? That would be counting to 1 trillion in 1 second. Well, a femto, well, an atto is, you know why an atto is significant right now? Do you know who won the Nobel Prize in Physics in 2023? These guys here won it. And do you know what they won it for? They made a laser that pulses with light pulses of 1 attosecond. Can you imagine that? And so how many pulses of light is that in 1 second? In 1 second, that's 10 to the 18. 10 to the 18th is a billion billion. Can you count to a billion billion in 1 second? Well, that laser just pulsed 1 billion light pulses. Can you imagine that? Why do you need something that fast? They need a laser that fast so they can watch things that happen very quickly. Like us, we could watch the combustion a little bit because we saw the blue. You know, what was the blue? Yeah, and well, the blue was, there's a whole bunch of stuff happening. There's violent collisions in the plasma, and the violent collisions creates reactive species, and these reactive species don't live forever. They have a very short lifetime. Some of these reactive species have a lifespan that's shorter than a picosecond. So if you blink your eye for 1 picosecond, it's gone. You know, it was there and now it's gone, but you didn't even see it because you blinked. Well, with an attosecond laser, you're only going to blink your eye for 1 attosecond, and so you might not miss it. So in 1 attosecond, it still could be there. And so they're using this to probe that stuff, these ultra-fast reactions. But anyway, I got to stop here because I need to do one thing, and that is we're going to have another quiz. Okay.